And now I get to run my class. So those of you at home do not understand what that quote is referring to. All right, so today we're going to finish off the proof of the prime number theorem. Proof should definitely be in quotes. This is not a rigorous exposition, but this is trying to give you the broad brushstrokes of how complex analysis enters and why we care about the location of the zeros of the Riemann zeta function. So the main idea was we looked at zeta prime of s over zeta of s. We took its logarithmic derivative. We multiplied it by the test function x to the s over s. We did a contour integral, 1 over 2 pi I. And we related this to 1 over 2 pi I. The integral, we switched the order of summation. We had a lambda of n, the integral of x over n to the s ds over s. We started off with the real part of s equals c, which was greater than 1. This is over here. Real part of s equals c is greater than 1. And what we saw is on the right-hand side, if n was less than x, this integral was 1. If n was greater than x, it was 0 by contour. Over here, we get things related to the sums of the zeros and the poles. And so this gave us x coming from the pole of the Riemann zeta function at 1 minus the sum over rho of x to the rho over rho equals the sum of n less than or equal to x of lambda of n. And the main term of that is the sum of p less than or equal to x log p. And then we have the lower order terms involving the prime powers. The contribution from all of this stuff is big O of x to the 1/2. We have to be a little bit careful in terms of how we do this sum. That's why I put things in quotes. We're doing things with limits. It turns out you want to pair the zeros with their complex conjugate. What's going on here is 0, here's 1/2, here's 1, here's c. We start off on this line. We truncate at some point. We go off in some giant contour like this. And then by this classic results in complex analysis, the integral along this line is equal to the integral along these other three, plus the integral along these other three is equal to the sum of the residues inside. And this is where the Riemann hypothesis comes to play. We know that there are zeros at the even integers. This comes from the functional equation of the Riemann zeta function, the fact that we have a factor of gamma of s over 2. The gamma function has poles at the negative integers. Therefore, since it's gamma of s over 2, that will have poles at the negative even integers. The zeta function will cancel that out, so the zeta function must be 0 there. Well, when I'm trying to estimate the contribution, x to the negative 2, x to the negative 4, x to the negative 6, those are not going to significantly contribute. And in fact, as a nice exercise, you can write down exactly what this sum is. It's going to involve a logarithm, something on the size of log of x. So it's going to be very, very negligible. Well, actually, log of 1 over x, I think, or 1 over x squared. If rho is the 0 of the Riemann zeta function, so is rho bar, so is 1 minus rho. So if we had a 0 off the half line, if it was before the half line, there's a corresponding 0 after the half line. So in some sense, the best we can do in terms of making the error as small as possible is for all the zeros to lie on the critical line. And that's the Riemann hypothesis. And if that's true, then the sum of log p is going to be x. By partial summation, this gives us the number of primes is about x over log x. We expect the error term to be of size square root of x. There's lots of nice ways to look at this. One of my favorites is that with probability 1, the Riemann hypothesis is true. I will give you a probabilistic proof of this using the central limit theorem. So the probability a number is prime, so probabilistic proof of the Riemann hypothesis. 1. N is prime with probability 1 over log n. So we're going to just flip a coin. You can do a better model than this. And in a better model, you would actually take into account, if 3 is prime, what number will not be prime? 6. So in this model, I could actually have 3 and 6 be prime. You can make the model better. This is good enough. So n is prime with probability 1 over log n. So if you want to count the primes up to x, let's let x n be 1 with probability 1 over log n, 0 otherwise. If we now look at the new variable x, which is the sum n less than or equal to x of xn, we can take the expected value of both sides. And in probability, you learn the expected value of a sum is the sum of the expected values. This will give us the sum n less than or equal to x 1 over log n. Well, a sum is approximately an integral, so this is like the integral of dt. I told you this was rough, over log t from 2 to n, which is about, 2 to x, which is about x over log x. You're actually getting the correct main term. You want to know, how do you calculate your error in counting primes? What do you calculate? For those of you who've taken probability with me, if I want to know how much I'm off by, I would look at the variance. So if you calculate the variance, I'll leave that as an exercise, you'll get the variances of size x, so the standard deviation is of size square root of x. Standard deviation is of size square root of x. So here is a proof of the Riemann hypothesis with probability 1. If you choose any random sequence of numbers with the correct distribution for density, the prime number theory density, you'll get the prime number theorem. Well, of course, in some sense, this almost seems like a circular argument. Well, that's not surprising in complex analysis. But the reason this is not so circular is we're not saying that this is the density of the primes. We're just saying, imagine we choose a sequence like this, what would we get? If the density truly is like this, we get the prime number theorem. Well, if I assert that this is the density of the prime numbers, of course I would get the prime number theorem as the main term, because I've forced that to be my density. It's no longer math, it's just definitions. The content is the size of the fluctuations, the size of the error terms about x over log x. That's where things really kick in. So again, if I assume my density is 1 over log n, 1 over log t, anything like that, not surprisingly, yes, the number of primes is going to be of size x over log x. It's the fluctuations about that matter. That's the content of the Riemann hypothesis. The Riemann hypothesis, the fact that these zeros have real part 1/2, is equivalent to talking about errors in counting the number of primes. The two sides are equivalent. You can either get a better formula for counting primes, or you can get better information as to where the zeros are, the Riemann zeta function. So this central limit theorem argument over here, telling you that you expect the error term to be of size square root of x, you could interpret this as some evidence for the Riemann hypothesis.
Isn't there an underlying assumption that the primes are independent?
Oh, yeah. Yeah, I mean, this is a very bad model in many senses. Now, you can fix this a little bit by doing a better method of random primes, where if you declare n to be prime, you throw away all multiples of n, and basically generalize the sieve of Eratosthenes. And so if you do that, this would be a little bit better argument. The question is, are the primes special? Is there anything the primes have that a random sequence of pseudo-primes don't have, or random primes don't have? Can you think of a property the primes have that you don't have in general?
Most of them are odd.
Wow. Yeah, and most of them are not multiples of 3, except for, well, I can modify that as well over here. But there's a key property the primes have that the random sequences do not have. And it allowed us to do all the stuff we want to do with the Riemann zeta function. What do we love to do?
Oh, unique factorization.
We have unique factorization. It allows us to take logarithms. It gives us the Euler product. The only sequence where you have unique factorization is the primes. So this is a result that is true with probability 1 for generic sequence. If you choose a generic sequence, are the primes generic? Hell no. No. The primes are very special. Now, you would hope that that specialness would actually help, not hurt, but we don't know that. It does give us the Euler product. And later today, we will talk about Dirichlet L-functions. We will talk about ways to generalize the Riemann zeta function to other functions that will also give us information about problems we care about. It turns out if you don't have an Euler product, there are situations where the Riemann hypothesis fails. We actually think the Euler product is a positive, not a negative. We think it is actually evidence for why the Riemann hypothesis should hold. We think all good L functions should have an Euler product. But this is at least a rough heuristic as to what's going on. So I'm going to quickly review the proof that the Riemann zeta function does not vanish when the real part of s is greater than 1. And then we'll go to the real part of s equals 1. So lemma, zeta of sigma plus it does not equal 0 if sigma is greater than 1. So this was a homework problem. We haven't discussed this in class, correct? OK, so one way to look at this is zeta of sigma plus it is the product over all primes of 1 minus 1 over p to the sigma, p to the it, inverse. And what I want to do is I want to show that this is not 0, so we just have to bound this above from 0. So if I look at the absolute value, zeta of sigma plus it, this is the product over primes. And now the worst case for us is if for every choice of t, p to the it is, do you want it to be positive 1 or negative 1?
Negative.
All right, so we'll see if that's right. 1 plus 1 over p to the sigma plus it, and then we have an inverse on the outside. So if we have this as a sigma, as a positive 1, we're making this expression larger, so its reciprocal is smaller. Good. So this will be a lower bound. And now, in fact, I'm sorry, we've dropped the it. So we've put the absolute values inside. This is the worst possible case for us. And so it turns out it's sufficient to analyze this case. What would this mean? This means no matter what choice of p you have, p to the it is equal to negative 1. Is there any choice of p such that p to the it is always negative 1? Let's do something easier. Is there a choice of t such that p to the it is always plus 1?
Yes.
Yes. Take t equals 0. Can we make it always negative 1? This is p to the it is e to the it log p. So for this to be negative 1, t log p has to be pi plus or minus 3 pi plus or minus 5 pi. There's got to be one choice of t that's going to work for every prime. There's no choice that works. All right? So we will never be able to have this happen every single time. This is fine. This is common practice in number theory. Assume the worst possible case. And if you're OK in the worst possible case, then there was no need to be clever. So do not do needless thinking. Okay? There's no need to look at this problem more carefully. This is sufficient. So now what we're going to do is we're going to multiply by 1. So we multiply by 1 minus 1 over p to the sigma inverse over 1 minus 1 over p to the sigma inverse. So multiplying by 1 is one of our most useful techniques. When we multiply by 1 over here, we get 1 minus 1 over p to the 2 sigma. And now this thing over here in the denominator, so when the dust settles, we get zeta of sigma plus it is going to be zeta of 2 sigma over zeta of sigma. This part over here is going to be the zeta of 2 sigma. And then we just have the zeta of sigma along for the ride. This is beautiful. We know when we choose s to be a real number greater than 1, the zeta function is clearly non-zero. Because zeta, let's call it eta. Oh, that would be horrible with the letters we'll do r. We'll do x, even though it's painful to do that. Is going to be 1 plus 1 over 2 to the x plus 1 over 3 to the x. And this is greater than 0 if x is greater than 1. And it's also finite. So we know the zeta function is not 0, and it's not infinity if we choose the real part of x greater than 1. Yes?
You have like a greater or equal to?
Oh, sorry, yes. This should still be, yes. That should still propagate down, yes. And so over here, we know that this now has to be positive.
Do we want those to be less than or equal to?
Over here?
Are we trying to bound? Oh, no.
No, we want to bound this above 0. So the zeta function is bounded from below. We have to worry about could it be infinity as well? Could it have a pole? But I will leave that calculation. That's not so bad. This is easy. This is really straightforward. Some of you had another proof of this in your homework. We used logarithms. I like this proof because it multiplies by 1. It also allows me to talk about a paper I wrote a couple of years ago where I was analyzing a large number of Euler products. And the key observation that allowed us to figure out what to do was that by multiplying by 1 in a clever way, we could see zeta functions and L functions and pull them out. And so it's often useful to do something like this. This is a very nice trick. 1 plus 1 minus reinforces to 1 minus with a square now. So this piece over here, the fact that this is becoming a 1 minus 1 over p to the 2 sigma inverse. That's really nice that it combines.
Is it all, would it also be sufficient just to find the value or the factor in there that's the least and then show it's not 0?
Well, no, because what if I have a bunch of factors that are getting small and small and smaller?
Well, and also know that they're tending to 1 as p gets larger.
But you've got to be very careful about the rates. So if I do n over n plus 1, and I take the product. So this would be 1/2 times 2/3 times 3/4 times 4/5. And if you look at that, that converges to 0. So even though all the factors are less than 1, they're converging to 1 so fast that the final product is actually going to be 0. And we looked in class instead at the product of n squared over n minus 1, n plus 1. And that was finite. So let's see if I do 4. I think that equals 2. And so, huge difference in terms of how these things can go. The main thing to note was that this could all be done very simply on one board. Okay. Does anybody know what the official name of this course is? Advanced analysis. Right? Oh, I booked the. And that must be anger. Where else have you heard AA?
Abstract algebra.
Abstract algebra, okay, in a non-math setting. Yes, Alcoholics Anonymous. Now, typically, if you're an alcoholic, how long does it take you to recover?
4 steps.
How many steps? 12. Okay? 7. We only need 7 steps in number theory. Okay? Much, much better than alcohol. Okay? Although, actually, I've got to be very careful because this is being recorded. So I will not mention that there is a student working with me on a project that will require me to buy Tennessee whiskey and Kentucky bourbon for a paper we're working on. What we're going to do is we're going to show zeta of s does not equal 0 for real part of s greater than 1. We can replace the greater than with greater than or equal to. This is a minor change, but it turns out this is equivalent to the prime number theorem. So we saw from the arguments before, when we were trying to do the calculation, that we do the contour integrals, it's the location of the zeros and the poles that really matter. If we don't have any zeros of the Riemann zeta function on the line real part of s equals 1, that's very good. What does that mean? So here's 0, here's 1/2, here's 1. So if there's no 0 on this line, then what you can do is you could have maybe a chain of zeros getting very, very close, but no zeros actually on the line. And so when we do our contour integrals, when we break things up at a finite height, we would have the 0 would be off by a little bit, and we have just a little bit of savings in the sum of x to the rho over rho. Now the problem is the real part of these zeros could be approaching 1. We actually have what's called zero-free regions. And they look something like this. And the thickness here is disgraceful. I forget exactly what it is, but it's something like 1 over the log of like 1 plus t, an absolute value, to some power. That's the thickness. So as you go higher and higher up, the distance which you can walk away from the line and not have a 0 of the Riemann zeta function is getting very small. Or it may be a log, I don't remember. It's not a great result compared to what we think the truth is. We think the truth is a half. As t gets very, very large, this is nowhere near a half. Why do we write it as the log of 1 plus absolute value of t? Log of 1 is 0. So maybe I actually should write it maybe as log of 2.
No, I thought you were asking why is it plus absolute value of t as opposed to.
Well, no, I mean, for instance, if t equals 0, if we were at the very beginning, we would have an infinite, we would have the log of 0. which would be a big problem. So if t equals 0, then the smallest this would be the log of 1. The log of 1 is 0. So probably we maybe should write this a little bit more. Maybe write it as the log of 2 plus absolute value of t. That way it's going to be well defined everywhere. And you put in the absolute value so that it works both above and below. All right, so there are lots of different proofs that the Riemann zeta function does not vanish on the line real part of s equals 1. I'm going to go through not the original proof, but a later proof due to Mertens. And this is the 7-step proof, 5 steps better than. It revolves around an incredibly clever identity. And so I tried to write the stuff over there so I could still see the cosine of theta minus 1. So this is step 1, is greater than or equal to 0 for all theta. This is not hard to prove. Right? I've given you a real number and I'm squaring it. Okay? So if I write it like this is really not that surprising of a result. The thing that makes it useful is this is the same as 3 plus 4 cosine theta plus cosine of 2 theta. That's why this is useful. And because these are the same, now you get this must be greater than or equal to 0. So we talked in this class about how to prove every trig identity in 1 minute or less. So you can figure out all these different formulas. You can expand things. You get a cosine squared. And so there's lots of ways to connect them. So one thing is proof cosine of 2 theta is cosine theta plus theta. This is cosine theta plus, minus sine theta sine theta. Well, sine squared is 1 minus cosine squared, so this gives you 2 cosine squared theta minus 1. So you can now solve for cosine squared of theta in terms of cosine of 2 theta. And you just put all that stuff in here. So it's now just algebra. Algebra is uninteresting to do in public, so we will not do algebra in public. But you can now just finish the details from that. Okay, step 2. Step 2 is more interesting. And in step 2, we're going to use our expansion. So we're going to take the log of the Riemann zeta function. The goal at the end of the day is to study primes. And so we have 2 ways of representing the Riemann zeta function. We have it as a sum over integers. We have it as a product over primes. Not surprisingly, if you're trying to prove things like the prime number theorem, it's the product over primes that's more useful. So step 2, expansion. So the log of zeta of s is the negative sum over all primes of the log of 1 minus p to the minus s inverse. Okay, let me see, do I want the log of zeta or do I want the log of zeta prime? All right. And so now we have lots of different ways of expanding this. We'll use the log of 1 minus x is equal to negative x minus x squared over 2 minus x cubed over 3, yada, yada, yada. Oh, the minus sign is going to cancel out very nicely. And so we get the log of zeta of s is going to be the sum over primes, the sum over k, and then we'll have p to the minus ks. Oh, sorry. So we're taking a look. I think that dropped. Okay.
Second sum should be over k.
And the second sum should be over k, not over p twice. Okay. So we have a very nice expansion like this, and then I think I should have a 1 over k coming from the stuff in the denominator down there. Okay. I think that's all the terms I'm supposed to have. Yes. Well, we can write s as sigma plus it. And so if we do that, we get the log of zeta of s is the sum over p, the sum over k, 1 over k, p to the negative k sigma, e to the negative, so p is going to be e to the log p, so we get negative k I t log p p. What's nice about writing it like this is the magnitude and this is the direction. And so in terms of doing things for the angle here is going to be like kt log p, maybe with a 2 pi or divided by 2 pi, depending on how you want to normalize things and define things. Okay? So we have an expansion for the log of zeta of s. This is just coming from the Euler product. So if I wanted to figure out what's the real part of this, if I wanted the real part of the log, I would just have to take the real part of this. Well, the real part of this is just to take the cosine term here. Right? If I want the imaginary part, I would just take the sine part here. It turns out for the logarithm, the real part is often more useful. The real part controls the magnitude. So if I have some number, if I look at the log of r e to the I theta, this is the log of r plus I theta. If I've defined my logarithm the right way, if I'm in the right region, this is not a class that assumes complex analysis, so I'm not going to go into all the details. But you can see the real part of the log of this number is the log of r. It's the log of the magnitude. So we can see that the real part is going to be what we care about if we want to study the size of the zeta function. And we're trying to show that the zeta function can't be 0 on the line. Okay? So it seems to make sense that we're going to want to look at something controlling its magnitude. All right, so we've done step 1, we've done step 2, we've talked about step 3. Let's just isolate it now. Step 3, the real part of the log of zeta of s is just the sum over p, the sum over k, 1 over k, p to the negative k sigma. Then it'll be cosine of kt log p. Okay? Right now, it's not entirely clear why we're doing all of this. What's going to be useful is that we're going to look at a great combination of products of zeta functions together. And that's going to win the day for us. Right now, we're just trying to get a sense of what the magnitudes are. If you think about this, this is very similar to what we did at the start of class today when we looked at the zeta function to the right of the line, when we looked at the zeta function where sigma was greater than 1. We wanted to try to understand how big could it be. We looked at the worst possible case, which was worse than what would actually happen, and we used that to get some information. Here, we're just trying to get to the point where we can understand what's happening. All right, now the next thing is we can look at the following combination. 3 log zeta of s, I think we'll do sigma. Let's do sigma. Plus 4 real part log zeta of sigma plus it plus the real part of the log of zeta of sigma plus 2it. What can you tell me about this monstrosity? What kind of number is it, first of all? It's a real number. Do you think it's an integer? Almost surely not an integer. Do you think it's irrational?
Irrational?
Irrational.
Irrational?
No. I mean, probably there might be some choice of t that makes it. There will be by continuity. Okay. Is it a complex number? Does it have an imaginary component? No. Here, sigma, I've got a real number. Zeta of sigma is real. I'm taking the real part of something. Okay, the real part of something is real. I'm taking the real part of something else. The real part of something else is real. This is a real number. What kind of real number is it?
Non-negative.
It's non-negative. How do you know it's non-negative?
Because you have that formula over there.
Because of this formula over here, 3 plus 4 cosine theta plus cosine of 2 theta. So we're basically, what we're doing is for each prime, for each k, we have a cosine kt log p. In the first case, when we have zeta of sigma, that's the case t equals 0. In this case, we have theta will be kt log p, and in this case we'll have 2 kt log p. So for each prime, for each k, so we use property 1 for each p and k, and we take theta to be theta sub pk, which will be kt log p. And so this combination has to be non-negative. So this was Mertens' great insight, is that this combination is non-negative. Okay? Now the question is, why do we care that this combination is non-negative? What do the real parts, what are the logarithm, if you take the logarithm of a complex number and you look at the real part, that's basically its magnitude. Well, it's magnitude up to exponentiation. So we could exponentiate backwards. And so we can use this to get some information about the size of a product. So we're almost there. So now what we do is step 5. We get zeta of sigma plus it to the 4th, zeta of sigma plus 2it. What can we say about this? We know the real part of the logarithm of this is non-negative. So what can we say about the magnitude of this quantity?
Greater than or equal to 1.
It's greater than or equal to 1. Real part of log is non-negative, so exponentiate and at least e to the 0, which is 1. Now, hopefully it's kind of clear why we were doing all of this. Is the great idea was to look at this combination of zeta values together. This is in some sense the very first example in this class of the notion of a family. And this is, if we get into random matrix theory and L functions and random matrix theory, this is going to be a huge subject for the course if we go that direct route. This is a huge subject in mathematics right now, that it's often best not to study L functions or to study quantities in isolation. You want to study them together. Why do you want to study them together? You have the advantage of averaging over things. So allows averaging. If you just have one quantity, what it is what it is. But when you have many things, you can play them off each other. You can execute sums. You can get some kind of cancellation. And so again, you can read the proof. You can go through the details. What I want to do is I want to highlight what's really going on here, what was really clever about this proof. It's also using one of my favorite inequalities, that the square of a real number is greater than or equal to 0. The difficulty is choosing which real number to square. Right? Squaring 5 typically does not help you. But squaring cosine theta minus 1, that's a great choice. And then figuring out that if we look at our expansions, we can use that. All right, so is everybody comfortable through step 5? We're almost done, so if you want a drink, you better have it fast, because we're running out of time. All right, we're all okay on this. So now, let's assume the Riemann zeta function actually vanished when the real part of S equaled 1. Let's imagine a horrible world where this was true, okay? If that was true, then what we could do is let's choose t to be the correct ordinate. So let's assume that there's a 0 at 1 plus it. And that's going to be a specialty. Right now, this is true for any t. And right now, S has real part of S's sigma is greater than 1. Now what we're going to do is we're going to let sigma go down to 1. And we're going to choose our height to be the height where there's a 0. So assume zeta of 1 plus it equals 0. Let sigma go down to 1 from above. All right, well, if this is 0, then we know that the limit as sigma goes to 1 from above of zeta of sigma plus it has to look like a times sigma minus 1 plus something of size sigma minus 1 squared. That's what it's going to mean for the function to be having a 0. Okay. So what is that going to mean? What does this look like as sigma goes to 1?
Blows up.
It blows up. It blows up like 1 over sigma. Wait, I dropped a 3. I'm sorry, there should be a 3 over here. Sorry. Right, because we had 3 times log of zeta. So this is going to look like 1 over sigma minus 1 cubed. This is going to look like sigma minus 1 to the 4th. All right, so as sigma goes to 1 from above, zeta of sigma looks like some other constant. Well, actually, we know what the constant is. It's 1. 1 over sigma minus 1 plus big O of 1. So the zeta function is looking like a 1 over sigma minus 1. We get that cubed. Over here, we have a sigma minus 1 to the 4th. Yes?
What's that A of sigma?
Just there's some constant. Some constant. If you want to be really pedantic, I could put a subscript t to denote that it's going to be coming from the fact that we're moving at height t. What matters is that t is fixed, and so it doesn't really affect what happens. All that really matters is as it has a 0, it's got to look like sigma minus 1. Okay, so now that we have this, all that's left is to just put all the pieces in together. Try to get the camera to move over. All right, so all that's left is to now put the pieces together. So we combine. And when we combine, as sigma goes to 1 from above, our product, which is greater than or equal to 1, looks like 1 over sigma minus 1 cubed, a of t times sigma minus 1 to the 4th. What about sigma, zeta of sigma plus 2it? What does that look like?
Doesn't matter.
Doesn't matter. All we need to know is that the only pole of the Riemann zeta function is at s equals 1. There's no pole, and so the other piece, since finite, doesn't matter. So we are using a little bit of the functional equation of the Riemann zeta function. We know that the only pole is at s equals 1. So if there was a pole here, that would be bad. If there was a pole, that we've got a sigma minus 1 to the 4th, a sigma minus 1 cubed. This is looking like sigma minus 1. If there was a pole here, that could perfectly cancel the sigma minus 1, and then everything would be OK. But the net effect is that this is looking like some constant times sigma minus 1. And as sigma goes to 1 from above, what does this go to?
0.
Goes to 0. Contradicts that it's greater than or equal to 1. And there's the proof. All right. So this is a long, involved proof. There's a lot of stuff going on here. The idea is that if you had a place where you had a 0, you pair that up with twice that height, and then you look at those combined with just the Riemann zeta function going at the pole. And you have this triple product here. And the product, of course, has more than just 3 terms. It has 8 terms. The 0 here gets magnitude by a 4. The pole gets magnitude by a 3. 4 beats 3. Contradiction. So the Riemann zeta function does not vanish. Okay? Hopefully you will appreciate that this is a lot worse than just proving that it is not 0 if the real part of sigma, if the real part of s is greater than 1. There was a lot more work needed to just get this to greater than or equal to. If you now want to get a region where there are no zeros, a zero-free region, that's even more work. If you want to get to the Riemann hypothesis, that's beyond what we can do. And so what I hope you get a sense from all of this, and this is why I want to put it all together, is the difficulty as you keep increasing your knowledge of the zero-free region. The more you have, the more difficult it is to get there. But the more it will give you. And so it is worth doing this. A huge industry is trying to get the best zero-free regions we can get. especially when you look at families of L functions. Okay, any questions about this? Okay, so this was the 7-step program. All right? So what we can do now is we can talk about modifying the Riemann zeta function. I'm sure a lot of you have seen at least one modification, but I want to discuss other possibilities, and we'll see which are good and which are bad. So zeta of s is the sum, n goes from 1 to infinity, of 1 over n to the s. So let's generalize. Can somebody tell me a way we could generalize this?
Having an arithmetic sequence in the numerator.
So one thing is to say, well, you know what? What we really have is we have LSF is the sum, n goes from 1 to infinity, of a sub f of n over n to the s. We have some sequence of numbers in the numerator. What is the simplest sequence that I will let you look at? All ones, right? I will not study the sequence of all zeros. The sequence of all zeros is not particularly interesting.
Converges very fast.
Yes, in fact, that's called the zero function. Okay. All right. So one possibility is we could modify the numerator. What else could we do? We could modify the denominator. I'll call it maybe LSF is the sum, n goes from 1 to infinity, of 1 over f of n to the s. We could do that as well. Which do you think is better?
More interesting.
I'm sorry?
Like you more interesting.
More interesting, more useful for mathematics?
Probably the first.
Probably the first. How many of you have heard of the first? How many of you have heard of the second? Exactly. No, I used this when I was taking my general exam at Princeton. One of my professors, Peter Jones at Yale, told me that after you've been around the block enough times, if there's a result that should be true, you should have heard of it. And if you haven't heard of it, it's probably not true. And so I was asked, a group theory question, is the following an alternative definition? And I had read so many books in abstract algebra, because I never took the class, as I was preparing for my generals, I had never heard of this formulation. So I said, this must not be an equivalent definition of a group. I said, good, now give us a counterexample. But I mean, it gives you an intuition as to what's going on. After a while, you should have a sense of what is true. If you hear a result, does this seem reasonable? If it's so close to other things in the subject, you should be able to figure out whether or not it's going on. Okay. So very quickly, we'll start talking about Dirichlet L-functions. So this is the first generalization. So Dirichlet L-functions. Well, it stayed on this. All right. How many of you have taken a course in abstract algebra? And unfortunately, I have to keep my hand down. How many of you have not taken a course in abstract algebra? Wait, is it just me? Wow. All right, so interesting. Normally, I don't require abstract algebra as a prerequisite for this course, but if I'm the only one who hasn't taken it, I guess I will assume everybody in the class knows abstract algebra. I've taught it at least twice, so it's not so bad. So we'll look at the group Z mod MZ star. All right. So this is the set of all integers that are relatively prime to m. So this is the set of all nm equals 1 and 0 less than or equal to n less than m. We'll do it like this maybe. Right. I'm not going to worry if m equals 1, but. And of course, since we're doing things that are relatively prime, n is not going to be 0. Okay. We're often going to take the special case when m equals q, which is a prime. Why am I denoting a prime by a q? Why am I using q to denote a prime? Yes?
We're going to use P for the Euler.
Yeah, we're going to use p for the Euler product, right? The Euler product is far more important than this level here, so we're going to keep the p for that. So it turns out, in this case, Z mod MZ star is actually generated by some element. So this is a very important result. How many of you have seen this in your abstract algebra class? Right. So what we're going to do now is we're going to define group homomorphisms chi from Z mod mz star to complex numbers of absolute value 1. And we're going to have chi AB equals chi of A, chi of B. So it's going to be completely multiplicative. And we're going to have chi of 1 equals 1. Is there any other possibility for chi of 1? I'm sorry?
It has to do with the identity.
0.
It could be 0. So if I say it's a group homomorphism, and I'm saying it's also mapping to complex numbers of absolute value 1, it's got to be 1. So there's no other possibility the way I've phrased things. But if I just looked at this property that I want it to be completely multiplicative, I could send chi of 1 times 1, which is chi of 1, to chi of 1 times chi of, okay, so chi of 1 has to be chi of 1 squared. It could either be 0 or it could be 1. It turns out it is not that convenient to send chi of 1 to 0 because then
You have the stupid homomorphism.
you have the stupid, everything gets sent to 0, and if everything gets sent to 0, it's not that fun. It's not going to really be able to teach you that much. Sending chi of 1 to 1, that's useful. All right, so now we have the Euler-Toshen function. So phi of m is the cardinality of Z mod mz star. So it's the number of elements we have. It's the number of things that are relatively prime. And what we can do is we can extend chi to z by the following. Chi of little n will be chi of n mod m if n is relatively prime to m and 0 otherwise. And you can see that this is a good extension. It turns out if m equals q equals prime, the possible characters are all going to be of the following form. They send the generator to e to the 2 pi I L over q minus 1. So we have to map things to something of absolute value 1. As soon as I say absolute value of 1, you should be thinking e to the 2 pi I something. Then the question becomes, why is it L over q minus 1? Well, if you take the generator to the q minus 1 power, you get the identity element. So we know chi of g to the q minus 1 is equal to 1. So we've got to be sending ourselves to a q minus first root of unity. And it turns out that you can put in different values of L. So unfortunately, I think it's time's up, so I will let you think of what values of L can we put in there? And how many of them do we have? Then in Monday's class, we will go through and we'll talk about some of the consequences of now that we have these characters, what can we do? So we use the Riemann zeta function to count primes. We will use these characters to create Dirichlet L-functions, and we'll count primes in arithmetic progressions. And then we will really see the notion of a family coming into play. If you want to count primes, you can go into 3 mod 4. You can't do it with just one L function. You have to do it with a family of L functions. Okay.